Hello, welcome to lecture number 29. In the previous lecture, we found the form of the frequency of waves that are internal to the system that means these are internal waves, and we saw form of the relationship between the frequency of the waves to the wave numbers, which is also governed by the proportionality constant between a functional form of the wave numbers to the frequencies is given by the stratification frequency. So we saw that the wave number, the wave numbers combined appears in the denominator, that is the kx squared plus ky squared plus kz squared appears in the denominator, while the numerator has kx squared plus ky squared. And this gives rise to the fact that omega should always be less than equal to n. And there's a key observation that we said that we make it we made it in the last lecture. Now the non-hydrostatic term in our assumption in the governing equation, the non-hydrostatic term can be neglected if we have very small waves, that is kz squared is much less than kx squared plus ky squared. Okay, please remember that this combination of kx squared plus ky squared appears in the numerator, while the summation of the kx squared plus ky squared plus kz squared appears in the denominator. So in cases of very small waves, that is very large wave numbers, we can neglect the non-hydrostatic term, that is we can neglect the vertical accelerations. And what happens as a consequence of this? You can see kz, if kz is much greater than kx squared plus ky squared, that means omega is less than n. There is no possibility of omega being equal to n. So this is straightforward inequality that follows from the previous relationship between omega and n in terms of the wave numbers. So in this case, the horizontal wavelengths are much larger than the vertical wavelength. Okay, so we get a bound on omega, that is the frequency, in terms of the stratification frequency and the wave numbers. Fine, that is fine. This is a mathematical inequality that we have derived. Now physically, thinking about the physics of situation, what happens if we force a system which has a frequency that is greater than n? I mean, there could be a situation n is only a value which arises from the background density gradient. Now it can happen then that we have a forcing frequency. Let's say we have a tongue, we have a certain vibrating mechanism that vibrates much faster than the background stratification frequency. Okay, so what happens in that case? In that case, the disturbance does not have a time to propagate away. So this does not have time to propagate in the kinds of in internal wave form. However, it can happen, it will happen that, and it has been observed in the oceans, that if there are certain localized frequencies or disturbances which have frequencies much larger than the local stratification frequency, then these generate patches of turbulence. If omega greater than n, if our forcing frequency is greater than n actually, so let's write down, if omega forcing is greater than the stratification frequency, we do not see waves, we do not see internal waves, to be more correct, because the inequality does not allow us We have said that this is the condition that will always be valid. The inequality does not allow us. We do not see internal waves. Instead, they form localized patches. Instead, the disturbances form localized patches of turbulence. So we have not yet reached turbulence. We will study turbulence in the next module. And turbulence is something where the fluid is chaotically mixing, it's highly diffusive, dissipative, there are lots of vortical features, lots of vortices, so that's a rough definition of turbulence. So instead, I mean, if we have forcing frequency greater than n, then we see these local patches of turbulence rather than internal waves. Now, again, going further into understanding the properties of internal waves, we're trying to do some wave kinematics, which is actually essential part of this study. Now, to develop some further intuition, we orient our coordinate system axis in a way that the wave number vector lies on the xz plane. In this case, we will have ky equal to 0. So there is no loss of information in this kind of orientation. So let's say there is a wave which is traveling in a certain direction, and on my left hand, I mean right hand, is pointing towards the direction of travel. This is exactly what you see. Someone, as a physical observer, a camera or a human eye, will see that the wave is propagating in a certain direction. Let's say this direction, and there is a coordinate system that we can create, and coordinate systems do not come with the problem. It is generated based on our ease of understanding, based on the kind of analysis that we have to do. So let's say we have a 3D Cartesian system, and we have an x, y, and z coordinate system. So we have a wave which is traveling in a certain direction, and this is pointing in some random direction which is between x, y, and z. It's not aligned along any of the axis. Now we orient our coordinate system in a way that it lies only in the xz plane and nothing changes in the y direction. This can always happen because the choice of coordinate system is ours. It is not dictated by the problem, but it's dictated by how easy or how well, I mean, what is the analysis technique that we want to adopt. And for simplicity, we say that we are orienting in such a way that this wave lies only in one of the planes, whereas and any changes in this other direction, which is perpendicular to this plane that contains the wave, is 0. This is how we change our coordinate system. This is what we are doing. I mean, we are changing the coordinate system, just rotating the coordinate system, the axis. So in that case, ky will be 0. So this is in the modified plane, okay, and we are not writing down a different variable for the modified coordinate system. It could have been written down as x prime, y prime, z prime, but we are not getting into that because we'll be using that coordinate system very often. I mean, and we'll be probably we can use it. I mean, use those variables interchangeably, and I'll make it clear when we are using a rotated coordinate system. So then, in this case, omega squared equal to n squared kx squared by kx squared plus kz squared. Okay, that is omega is equal to plus minus n kx by square root of kx squared plus kz squared. Now let's see what this term means. What this ratio of kx by root kx squared plus kz squared mean? Kz is aligned along the z direction. Kx is aligned along the x direction, and let's say the angle between both of these is theta, and this is the hypotenuse. This is kx squared plus kz squared, the square root of that. And what does cos theta mean? Cos theta is kx by square root of kx squared plus kz squared. Now see why we had to do this trigonometric where to create this trigonometric relationship, because we can now we can now contract this whole system in terms of an angle of the horizontal wave number angle between the horizontal wave number and the wave number of the propagating wave. Okay, writing simply and more clearly, omega is equal to plus minus n cos theta. So theta is the angle between the wave number vector, that is square root of kx squared plus kz squared, with the horizontal direction. Okay, this means the frequency of the wave of the internal waves. This is important because this is interesting that we could express it in this way, and it's also important because frequency of the internal waves do not depend on wave number magnitude, but only its angle with respect to the horizontal plane. Okay, so we don't need the magnitude, the wave number, the magnitude of the wave number, but only its angle with the horizontal plane, that is its direction of propagation with respect to the horizontal. So this also means the above equation, omega and omega equal to n cos theta. This means the steeper the angle or the lower the frequency, steeper the direction. Of course, this comes from this triangle. Lower the frequency, steeper is the direction. So as omega goes to 0 in this limit, theta approaches 90 degree, that is purely vertical. So very low frequency waves have a very steep angle of propagation, whereas intermediate waves, intermediate meaning intermediate with compared to n, will have an intermediate frequency, intermediate angle of propagation. Okay, so here there is a brief detour that we need to do about wave kinematics, because it is important. It helps us in understanding the internal wave structure better, and this is also in general important for understanding multiple geophysical phenomenon, because of the fact that wave kinematics is at the heart of multiple situations in which because these appear in most of the governing as a solution to most of the governing equations that are being which actually represent multiple phenomena in the geophysical fluid dynamics within the geophysical fluid dynamics system. So basically, again, we need to do a brief detour of wave kinematics. We'll see what are the various quantities, that is the wavelengths and wave numbers and phase speed, and how we can define group velocity in a combination of waves. This is important because waves generally don't occur in isolation in real life in geophysical flows, and that gives us an opportunity to discuss to define a quantity called a group velocity, for which can appear which can happen in multiple geophysical flows. So there's a brief detour to in wave kinematics, and all of this will be helpful. We'll again come back to structure of the internal waves, because that is important for us to understand. But before that, let's do before looking at the structure, let's see the wave kinematics. So let any quantity of the wave be a sinusoidal function a. So we are defining any quantity. This could be velocity, this could be the amplitude. We are defining in a very general form cosine wave. Here capital A is the wave amplitude, this whole quantity within the cosine function, this is the phase, and this phi naught is the reference phase. So equivalently to this form, we can also represent the previous form as you can also choose cosine functions or sine functions. I mean, alternate. I mean, you can change the order. It does not really matter. So okay, here a1 and a2 are two amplitudes. So a1 is equal to a cos phi, phi being the reference phase, and a2 equal to minus a sine phi. And a can then be the real part of a1 minus I a2 e raised to I kx kxx plus kz z minus omega t, and this can be represented as ei phi. That is what the above A1 and A2 expressions give us. Now this might also be known to people, so this is, as I said, this is a slight detour for simple wave kinematics. This will be important. So assuming that there, I mean, there's a 2D coordinate system and we have a 2D plane wave. The wave number vector is pointing along this direction. It's a 2D plane wave, and the lines that I have drawn are the instantaneous phase lines. That means these are the lines at which the crest or the troughs are aligned at a certain instant in time. So this is a trough line, this is a crest line, this is a trough line. Okay, and this is where the amplitudes are maximum. So the trough is or rather the values, I mean the absolute values of the amplitudes are maximum. Trough it's minus a, in crest it's plus a, in trough it's minus a, and there are intermediate positions where the amplitudes are 0. So these are the positions where amplitudes are 0, and this is at one instant. T means trough, C means crest. Okay, and this wave number vector is aligned at a certain angle to x. Now let's write this, label these, actually should be some distances along each of the directions. So lambda is the wavelength that is seen by an observer, a physical observer, and lambda x and lambda y are the projections of this lambda along x and y axis. So these are instantaneous phase lines. So these are instantaneous phase lines of a 2D plane wave. So 2D plane wave with positive kx and positive ky. The observer sees lambda, and this is 1 by lambda, I mean by geometric relationship, 1 by lambda square is equal to 1 by lambda square, lambda x squared plus lambda y squared. Okay, and we define a quantity k, which is kx squared plus ky squared, which is called the wave number of the wave. This is the wave number of the wave. Okay, this, as I mentioned, this is a instantaneous phase length of a 2D plane wave, a single wave. However, I also mentioned previously that this these kind of, geophysical flows or real life situations can have waves, more than one waves. So what happens to the propagation speeds, what happens to energy propagation in those cases? So this is necessary because later on we'll use uh, concept of group velocity, and that is the reason why I defined wave number. I defined the wavelength for a single 2D wave, and let's see what happens with the 2D wave. We won't go much into detail, but we'll just say what happens when two waves actually they superimpose. So when we have more than one waves, where we have more than one waves, we will have areas of constructive and destructive interference. So we know from basic wave mechanics, constructive and destructive interference are when the waves either align perfectly and they are in phase, so they will add up their amplitudes, or destructive, they are out of phase with each other. So in that case, in the case of constructive interference, so wave amplitude and hence the wave energy is higher. Remember, this is a propagating wave, and this can have constructive and destructive interference as at different locations. So during constructive interference, the wave energy is higher, and during destructive interference, wave amplitude is lower, and hence the energy is lower. So destructive interference, wave amplitude, and hence energy is lower. So energy distribution due to the combination of these two waves is a property of the interference and the or the degree of interference and the degree of constructive and destructive interference. Okay, so it's a energy in the, is determined by how both of these waves interfere with each other. Okay, so it's a property of a set of waves rather than the individual waves separately. Okay, that is what we are getting at. So initially we are doing individual waves, whereas now we are looking at what happens to a group of waves. And energy propagation depends on how the interference patterns moves. How interference pattern how they move. Now, to see um, the movement of energy in the combination of waves. So let us take two waves. So let's consider two 1D waves of equal amplitude. And nearly equal wave number. So let's say we have waves of equal amplitude and nearly equal wave numbers, and this is what the combination of both the waves look like. And as we said, the combination of waves is a realistic possibility. And this um, in this situation, we have, as the wave numbers are nearly equal, we have delta k, which is equal to k1 minus k2. I mean, I'm taking the modulus of all of these, the absolute value of all of these, not caring about the signs now. So this is a constraint that we are putting, that this is much less. I mean, the difference in the wave numbers is much less than the mean value of the wave numbers, and the differences in the frequencies are similarly much less than the mean of the frequency of both the waves. Okay, so the above here, I mean, with the above conditions and this kind of a wave, the superposition can be represented as A equal to 2 capital A cos delta k by 2 x minus delta omega by 2 t times a second cosine function kx minus omega t. Okay, there is a first cosine function, there is a second cosine function. So this second cosine function is an average wave with wave number k and frequency omega, as you can see from this one. So this has a wave number k and frequency omega. Remember, this is not the frequency and wave number of a single wave. This is the average. This is the average wave number and the average frequency. I should have defined the variables here. So this is so k equal to k1 plus k2 by 2, omega equal to omega 1 plus omega 2 by 2. So these are the average of the wave numbers and the frequencies of both the waves in the system. Okay, and first cosine function, that is, this involves a much smaller wave number. As you can see, this is only delta k. Okay, this is delta k by 2, and we have a much lower frequency, which is delta omega by 2. As we mentioned previously, delta omega is much less than omega, and delta k is much less than k. Hence, this has a much lower wave number. That is, it's a much bigger wave. Means a bigger envelope, and the frequency is also very less. Okay, so the wave pattern in this combination of waves, which is given by this situation, is actually a burst or a group of waves which look something like this. Actually, this is not the best way to represent. I mean, this is not to scale. So we see a bunch of waves. This is not very good, but this is something to give you an idea. This is a bunch of wave packets or burst of waves, and in each of these waves, so within each group, the waves travel with omega by k, while the group travels with delta omega by delta k. For infinitesimal separation between the frequencies and the wave numbers, we can define a certain quantity d omega by dk. Now, given the fact that the energy propagation is a property of a set of waves, that is a group of waves which are bundled together, we can define this quantity to be a certain quantity of interest called the group velocity. And this is the velocity by which the energy propagates in the system. Cg is the group velocity of the combination of waves, and this is the energy associated with each group. So each of the groups will take away the energy at this group velocity, and this is different from the phase velocity, the phase speed by which the individual waves are traveling. So the first wave is traveling at a certain speed, k by omega, and then the second wave is traveling with k2 by omega, but the combination will give rise to a certain situation where there are packets of waves and the energy is being taken away in this by this velocity, by this ratio of the separation of the frequencies to the separation of the wave numbers. And we said that these are only one-dimensional waves. We started only one-dimensional waves. In terms of in 2D waves, we can define group velocities in each of the directions, del omega by del kx, and group velocity in the y direction. These are just, so these are for 2D wave. For two-dimensional waves, we can define group velocities in two different directions, and this was for a one-dimensional wave. So having learned this, we will go into understanding the internal wave structure from the next class onwards, and this is where we stop the basic discussion on wave kinematics. Thank you.